All right, welcome to part one of our lecture video series for Monday, April 24th, where we begin our foray in discussing what enthalpy is. And I remember when I first learned about enthalpy, it seemed like a really kind of useless term. Like it seemed kind of like a redundant thing, especially since we're going to be talking about heat and even using the word heat as a stand-in for enthalpy as we continue this conversation later. So what I want to do is I kind of want to zoom out a little bit and look at what we know about our thermodynamic descriptions and terms so far and kind of build the case as for why enthalpy is important. So to do that, let's go back to this idea of the total internal energy of a system. So the total internal energy for any system, in its most general sense, is the sum of all different types of energy that are found within that system. So this could be something like kinetic energy. This could be something like thermal energy. This could be something like potential energy. This could be something like electrical energy. This could be something like mechanical energy. There's a bunch of different ways that energy can be found, expressed, and transformed within some type of system. And what you and I have been doing up to this point has kind of been narrowing and kind of shaving off all these different versions of energy that could be found in any particular system into looking at what's just going on in a chemical system, right? So we've looked at the compression and expansion of gaseous materials, where that meant that the only terms involved in our total internal energy calculation was things like pressure, volume, work, and heat. But in general, the total internal energy involves literally everything, hence why total. So let's discuss or introduce this idea of enthalpy. Like, why am I zooming out on this idea of total internal energy in the first place? And in fact, let's go ahead and look at the change in total internal energy. So the change in total internal energy of a system, delta U. That's going to be the sum of all the changes in our different energies, like change in kinetic energy, change in thermal energy, change in potential energy. These are all summed. Yada, 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 just depending on what we've got in our system. And again, this is all what is wrapped up and found within the system. So this is all just like what's going on inside the system. So when we're talking about the change in total internal energy for some system that has maybe multiple different varieties of energy that are found, we are looking at the change or transfers meaning, yeah, transfers or translations or interconversions that are happening within the system and exchanging with the surroundings. So let's talk about what this means for enthalpy. So define the enthalpy of a system, H. Again, thinking about internal energy as like this sum of every different type of energy that could be found, or every different energy transfer mechanism that could be found within a system. Then enthalpy describes the amount of total internal energy that is required to generate a system and the amount of energy that is required to make room for the system. And when we think about this idea of making room, we're talking about a literal change in volume that is done displacing the environment around our system. So we've kind of talked about this when we talked about compression and expansion, but in enthalpy, we're talking about the total internal energy of our system. So whatever kind of energy translations need to happen to make our system what it is from start to finish. And then we're also including on top of that the amount of energy that is required to make room for the system by looking at the amount of energy that is required to establish the pressure of the system and the volume of the system via the displacement of the surroundings. So if I were to put this into mathematical language, I would see that enthalpy is the total internal energy, so that's U, that is required to make a system. So we're talking about some system as is right now when we're looking just at H, plus the amount of energy that is required to make room for the system by establishing some pressure and volume as a result of us working against our surroundings. So we're going to write this as PV, pressure volume product. Now, enthalpy is a state function, meaning we can use a delta to describe the change that is based only on the final and initial state of a system. So, meaning it doesn't matter how our internal energy is changing, nor does it matter how the pressure and volume of our system is expanding or compressing against some environment. We are just looking at the difference between initial and final conditions. That's what it means to be a state function. You'll hear this in Chem 220 as an equation of state. The idea is that state functions just depend on your final and initial state. So let's actually express enthalpy as a state function. So let's look at how the change in enthalpy might be expressed for some kind of system. So we're looking here at our conceptual definition. Enthalpy is the total internal energy required to set some system up. So we're going to look at the total internal energy that is changed as a result of undergoing some change in our system. So from for us as chemists, from reactants to products. And plus the amount of energy that's required to make room for the system. So we call this the pressure volume work. And this is our mathematical definition of the enthalpy of a system. Oop, I dropped a delta. Delta change, right? Pressure volume. Okay, now if you're like kind of tearing your hair out because you're like, wait, isn't this PV work essentially, this expansion, making room for the system, something we've already accounted for in chemistry? And you're absolutely right. Yes, like I gave us a very simplified definition of total internal energy because for chemical systems, we really only need to consider things like changes in thermal energy, so heat transfer, or changes in energy as a means of pressure volume work being done. But for example, if we're considering a chemical system with stirring, which has mechanical energy, and also electric potential, or you can think about this as almost like work that's done by the result of there being some electrical voltage setup, then I can look at something like an expression of my change in total internal energy being my change in my heat plus the change in my mechanical energy plus then also the change of my electrical work. That's not supposed to be Q, it's supposed to be W. And then the enthalpy of this system, which has kind of a lot more flavor in terms of what's in its total internal energy, would be the total internal energy, which comprises all of this stuff up here. And then in addition to that, how that system transfers energy according to some kind of compression or expansion against or from the surroundings. So just kind of a reminder that total internal energy of a system is not always heat plus work, right? And work is not always pressure volume work. That's just how we've been kind of reducing the parameters of a chemical system for our purposes here in Chem 210. When you get to physics and especially engineering, you're going to have to consider literally every flavor of energy that could be found inside some defined system. So this is why enthalpy becomes useful, especially later down the road in your future STEM courses. Now, the reason why I am giving you kind of this like zoomed out perspective of what enthalpy is because we're going to kind of collapse back into our little simplified realm of how we've defined total internal energy for a chemical system. And that is going to do some funky stuff because you'll see that we've got pressure volume work and also this delta PV term from enthalpy, and sometimes they might, I don't know, cancel out. So what I want to do next is I would like to, I don't know why I have this checked, I would like to look at how this enthalpy function and its meaning ultimately for us as chemists is going to be described for a system that's at constant volume. And then we are going to look at the enthalpy at constant pressure, which is, as mentioned kind of in our little lecture plan video, really the primary means that you and I have of thinking about enthalpy and conceptualizing enthalpy, and in particular measuring enthalpy in the lab. So all of this, what I'm doing now, is kind of lead up to get us to this point, which is what's kind of more practically realistic for us in Chem 210. And from that understanding of how enthalpy and heat and work and such are related at a system that is at constant pressure, then we're going to be able to get into heats of reaction and looking at energy transfer, specifically heat transfer, at systems that are at constant pressure. So let's move on into our next video where we can kind of look at how we can manipulate this equation of enthalpy for chemical systems. and particularly chemical systems at constant volume to start, and then we'll see where this gets us. So just hang in with me here when this conversation of enthalpy continues.